All right, let's talk. We're going to talk about something completely different today, or at least, new. We have been for a while talking about Euler circuits and various sort of, variations on the general theme of Euler circuits. Euler circuits, remember, are all about covering all the edges without duplicating any edges. All right. What I want to start talking about today, and we'll more or less be talking about this for the rest of our time together, which is not all that much. I want to talk about what we call Hamilton circuits. Hamilton circuits. So, unfortunately, you just have to remember which is which as far as the names. Euler circuit means that it uses every edge without repeating. Hamilton circuit means something else, is what we're going to talk about today. This is Hamilton. Hamilton is I believe an Irish mathematician. He lived in Dublin. Hamilton is famous for discovering what we call the quaternions, which is a four-dimensional number system. And he had this, he was thinking about the quaternions for a long time and couldn't quite figure out how it was supposed to go. And then one morning he had sort of like a revelation when he was out walking in Dublin, and he was at that moment crossing a bridge, and he carved into the side of the bridge the fundamental formula for multiplication of quaternions, which was his great discovery. And you can still go to this place, and there's a little sort of historical marker there, which has been referred to as the least visited tourist attraction in Dublin. So check it out if you are into obscure mathematical history. This is Hamilton, not the same Hamilton as the American Hamilton, politician and rapper. Although he actually did invent some mathematical something. There are mathematical things named after that other Hamilton, but anyway, this is not that Hamilton. This is the Hamilton from Ireland. Hamilton circuits, so this is it sounds very similar to Euler circuits, but actually the way that you deal with them is totally different. But anyway, a Hamilton circuit, this is the definition, is a circuit in a graph which visits each vertex once without repeating. All right. So it's the same as Euler circuit, but this is about vertices, not edges. All right. Euler circuit is about using every edge once without repeating. Hamilton circuit is about using each vertex once without repeating. And actually, in real life applications of graph theory, Hamilton circuits are a bit more useful, and they come up more often in real life than Euler circuits do, and we'll talk about why that is. But this is the definition of Hamilton circuits. And unfortunately, there is no simple theorem about you'll be able to look at a graph and you will immediately realize if there is or is not a Hamilton circuit. With Euler circuits, it's all about the degrees. Hamilton circuits actually have almost nothing to do with degrees, and it's a completely different question. If I show you a graph, is there an Euler circuit or not versus is there a Hamilton circuit or not? They're very different, and the Euler question is much easier. These are more complicated. But anyway, let's just look at some graphs here. I'm not trying to say Hamilton circuits are somehow harder, but because they're actually simpler than Euler circuits are. So this graph, is there a Hamilton circuit? Here, we haven't really talked about this at all, but we can just, by guessing or something, for example, is there a way to say start up here maybe and go around in this graph? You don't have to use all the edges. You just have to visit each vertex and end up back where you started. Can anybody see how to do that? I think it is possible here. Can anyone maybe describe how would you go around here, visit every vertex, come back to where you started? Is it possible? I think it is possible. Can you see how?
You just go
Yeah, just like go around. I mean, if you're understanding what I'm saying, this is very easy in this example. You can just like go around, right? So what I drew there is a Hamilton circuit. Right? It hits every vertex. It missed one of the edges, but that doesn't matter. For a Hamilton circuit, you just have to hit every vertex, and it should be a circuit, so it should come back to where you started. All right, that is a Hamilton circuit. How about, here's another, I guess, slightly more complicated graph. How about this? With one diagonal there. Is there a Hamilton circuit here? I think there is. And actually, even drawing Hamilton circuits, I mean like physically drawing them is just a lot easier. For instance, if I want to start here to indicate a Hamilton circuit, you know, when you're drawing Euler circuits, I had a fair amount of like coaching about your artistry, about how you draw the line. Actually, none of that is really necessary for Hamilton circuits. You can more or less just kind of, I'm going to make it thick here. You can just kind of say, here's my Hamilton circuit. Check it out. I think that one visits every vertex. And making it thick like this for an Euler circuit would be way too confusing, because an Euler circuit has to cover all of those edges and you wouldn't be able to tell what I was talking about. But actually for a Hamilton circuit, it's not an issue at all. Here you can still tell. The only thing I didn't indicate really is like which direction did I go around, but that kind of doesn't really matter. You can go either direction and it's a Hamilton circuit either way. So anyway, this is, whoa, I'm thick. The thickness. This is a Hamilton circuit, right? I mean, this graph has a Hamilton circuit, and what I drew in red is the Hamilton circuit. It visits every vertex once and doesn't repeat any vertices. It doesn't use all the edges, but that's not the point with Hamilton circuits. All right? How about if there was no diagonal there? You could try to do a similar thing. Here, I'll try starting here, maybe go around like this. Actually, what I have there is not a Hamilton circuit because I missed one of the vertices. So maybe I should have instead, I don't know, if I go over there instead, this is not a circuit, and there's no way for me to get back to the beginning without repeating any vertices. Actually, if you just try, maybe I do that. Okay, this also is a dead end. There's no way to get from here back to there because there's no edge right there. This one actually has no Hamilton circuit. It's not possible to make a Hamilton circuit in this graph, although it's not obvious, like why could you be convinced of that fact, other than just trying some stuff and nothing seems to work. But we need to talk a little bit more about how would you actually demonstrate this. But I will say this graph, it's true, and we're going to talk, today about how you could actually show this. This graph has no Hamilton circuit, and I will just say it's hard to say exactly why. Right? I mean, you can tell if you just sort of try to draw one in there. You can probably tell that it's not going to work, but it's not. If you actually wanted to convince somebody that it was impossible, it's not immediately obvious how you might do that. All right, just two more quick ones, and then we'll talk in some more detail about these. How about this guy here? You want to try this out? I will let you think for a moment. Can you find a Hamilton circuit in there? Or do you think, maybe there isn't one? But see what you think. You can start in any vertex you like. Maybe start in I always kind of start in a corner for no particular reason. But can you make a circuit that meets every vertex? I'll give you till the clock says 9:41. I'm going to walk around and see how you do.
so far?
Oh, it says 9:41. I saw some folks come up. There's actually two different ways to do it here. What I saw was something like go down and then across here and then something like this. These ones you can draw really, I mean, I know not everybody has different colors, but you can just kind of scribble in certain edges, and that describes a Hamilton circuit. It visits every vertex. Some people had basically this but upside down, and that's works out great too. Anybody have something else? I think those are the only two possibilities for this. Either that what I drew or that same thing but upside down. Yeah, great. Okay, so this one has a Hamilton circuit. All right. One last example. This one does not have a Hamilton circuit, and I think maybe you'll be able to tell. So in this case, I have two vertices on the left and 4 on the right. And I'm going to connect everyone on the left to everyone on the right. So the top left goes to all 4 of the ones on the right, and the bottom left also goes to all 4 of the ones on the right. Now some of the lines are crossing, but those I'm not trying to put extra vertices in there. So there are only 2 vertices on the left, 4 on the right. Those lines crossing are just lines crossing. They're not extra vertices. All right. This one actually you can tell definitely does not have a Hamilton circuit. If you think about if you're going to draw, say my red line in here, you have to, let's say I'm going to start here. Your first edge has to go across to the right. Now you could go to the top one or to those 3 other ones, but it has to go from left to right. And then your next edge has to go back to the left. So maybe I would have to go back to the left. And then my next edge would have to go back to the right. And at this point, I'm stuck, right? There's no way to go back to the left again. So because in this graph, every path that you draw has to go back and forth. You actually can't go back and forth without repeating some of the ones on the left, because there are not enough on the left to go back and forth, 4 times and hit all of the vertices. So this one has no Hamilton circuit. This is because going back and forth, which is how in this graph, those are the only way to make a path, is to go back and forth, left to right. Going back and forth here will force you to repeat some vertices on the left, right? Because you have to go back, to hit all the ones on the right, you got to go back and forth 4 times, but there's not enough on the left to actually make that possible. So this one you can explain that it is impossible to make a Hamilton circuit in that guy. All right. But this is a very specific sort of type of graph, and usually it's going to be a little bit trickier to decide how to find if there is an a Hamilton circuit or not. So that's what I want to talk about for our time today. I will say, so how to tell is the big question. How to tell if a Hamilton circuit exists, and how to find it. Actually, these for the case of the Euler circuits, these are completely different questions. How do you know if it exists or not? And then how do you actually draw it in? For a Hamilton circuit, it kind of involves the same procedure. How to tell if a Hamilton circuit exists? I will just say, first of all, there's no theorem that makes it simple. In the case of Euler circuits, there's the theorem, Euler's theorem about Euler circuits, which is just about, you look at the degrees and see if they're even or not. But there's no simple rule like this for the case of Hamilton circuits. If you look at all of these examples we've already talked about, none of these make any sense if you try to think of these in terms of the degrees. The degrees really have nothing to do with anything in these examples. So there is no theorem that makes it easy, unfortunately. And so what we have instead is just sort of like a collection of basic facts, a few basic facts about about Hamilton circuits. So first of all, one basic fact, and you can see this in all of the examples that we've done so far. When there are Hamilton circuits, look at the red line here, for instance. It goes through a bunch of vertices. You will notice, and similarly for the red line here, if you only consider the red line, every vertex has sort of a degree 2 if you are only considering the red lines into it. Every vertex is visited by 2 of the red edges, right? This is a basic fact. It's just because this circuit has to visit every vertex only one time, which means it has to arrive once, leave once, and that's it, right? So the red, the chosen lines or the chosen edges meet each vertex twice. So I'm going to write that like this. Each vertex meets exactly two of the chosen edges, what I've been drawing in red. I don't know how you've been drawing it in your notes, but it is a fact. When you have a Hamilton circuit, each vertex meets 2 of the chosen edges. I'm going to put this sort of in a box. This is the first of our basic facts. There's basically 2 of these basic facts. Each vertex meets 2 of the chosen edges. That is the edges that I draw in red. Actually, this very simple observation will help you a lot to create Hamilton circuits in a graph. So, for example, this actually lets us start, at least, drawing in our Hamilton circuit immediately. No guessing, right? The one I asked you to do a few minutes ago, I intended for you to just kind of look at it and sort of figure it out by some kind of guessing or common sense. But if you remember this fact in the box there, it lets you start drawing your circuit immediately without making any guesses. For example, if I have this graph, how about that? And I would like to know, as usual, is there a Hamilton circuit or not? Now, it's not so hard to guess, but I am going to try to do this with no guessing. Because of this, of the 2 edges thing, we can draw in some red edges automatically. For example, if I look, say, focus on the vertex right in the middle, and you know 2 of those edges are going to have to be picked when I make my Hamilton circuit. But actually, there's no way of telling which of these 4 are going to be the 2 that I end up drawing in red, right? But for some of these vertices, like for this one, there's only 2 there, which means I'm going to have to use those 2 as part of my red edges, right? So right here, looking right here, actually this does have something to do with the degree. That is a degree 2, which means there are only 2 edges there, which means I must use those 2 edges as part of my Hamilton circuit, right? Because that circuit has to go through that vertex, there's only 2 choices, and so it's got to use those 2. And I can see 2 other vertices which are degree 2, and for the same reason, here and here, we also have to use this edge and this edge, and we have to use that edge and that edge, all right? We can draw in some red edges automatically. And the basic idea here is, I mean, you can say this very clearly, if any vertex has degree 2, then both those edges must appear as part of the Hamilton circuit. As part of the Ham circ. All right? If any vertex has degree 2, then you have to use both of those edges. So this is actually the only time in which the degree really matters for the Hamilton circuits. Other degrees are not so important, and the issue of like even versus odd is not very important. It's just about 2. There's a special thing if you see vertices of degree 2. Both of those edges must appear as part of the Hamilton circuit. And so now this, what I've drawn here, is not a complete Hamilton circuit, but at least it's getting me started without having to do any guessing. And maybe from here I could say, well, all right, now I'll have to guess the rest of them. By the way, does anybody see how to fill in the rest of the Hamilton circuit? Given that you have to use these guys, anybody see which other ones to use? Like for instance, right in the middle here, I'm gonna have to pick 2 out of these 4. You wanna see how to do it? Nobody's saying anything. All right, have it your way. We'll come back to this. Maybe you can see it and you're just not saying it. If you see something, say something, right? They always say. Okay, can we talk about our remaining sort of fun fact? You know, I said each vertex meets 2 of the chosen edges. So what that means is, it means this. If any vertex has degree 2, then both of those edges must appear as part of the Hamilton circuit. It also means, to go a little further than this, for example, right here, since this vertex, I have already chosen 2 edges there, it means I cannot also use that one. That's because a Hamilton circuit, when you look at the full Hamilton circuit, like look in all of these examples, there's no such thing as a 3-way intersection of the reds. That's because that would constitute revisiting the same vertex again, and that's not allowed. So this business about each vertex meets 2 of the chosen edges, that means it meets only 2 and not more than 2. So also, if any vertex has degree 2, then both of those edges must appear as part of the Hamilton circuit. And also, no 3-way intersections are allowed. In a Hamilton circuit. So, if some vertex already has 2 chosen edges, we can exclude all of its other edges. These are basic strategies here. And these 2 kind of are an expanded version of what I said before about each vertex meets 2 of the chosen edges. Each vertex meets 2. That means if you ever see 3 edges, but already 2 of them are being used, you can't use the 3rd one. We can exclude all of the other edges. So what that means, as far as this picture goes, I'm going to copy this again, just so that it's clear step by step what I'm talking about. This picture here, come on now. There we go. So given that we already have this much, we can exclude this edge right there. It's because if I look at the vertex at the bottom there, I see already I have chosen 2 red edges there. You can never have three-way intersection among the chosen edges, which means that other edge can never be used as part of my Hamilton circuit. And I see one other place where this happens. What I'm looking for is a vertex where I've used 2 edges already, but then there's another edge there. I see that right here also. I've already used these 2 edges, which means that this 3rd one cannot also be chosen. So these 2 here, we can exclude these edges. That and that. All right? It's because those 2 vertices that I circled already had 2 edges chosen through them, and that means you can't choose any more than 2, and so those edges are excluded. All right? And the way that you do this generally in terms of if I show you a graph and say find me a Hamilton circuit, it's like sort of doing a little puzzle where You start by scribbling in some of them that you're going to use, and then based on that, you can exclude some other ones and say, I definitely can't use some of these. It's a little bit vaguely like playing Minesweeper or something, where it's all about like, you decide, you're trying to move somewhere and you decide, I can't go here, here, here. That means I can go here, 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 and that means I can't go here and here and here. I don't know if you know what I'm talking about. Minesweeper is a classic game back in the day when life was a lot more boring. We used to play Minesweeper because we had nothing else to do. So anyway, because of these two edges, you can exclude those two. Now, because I excluded those two, if now I look at the center vertex, there are only two remaining edges which are allowable to use, and so we must use those two remaining edges. So now, I'm going to try to write this in words. At the middle, only two legal edges remain. So we must use those. And so this picture again, I'll copy it again. At this point, if you look at the middle edge this time, so now I'm looking here, there are only now two legal edges which can possibly be used, which means we have to use those two edges, there and there. And now we're done. This is a Hamilton circuit because it covers every edge. It meets every vertex. It does not cover every edge, but that's fine. That's not the point of a Hamilton circuit. All right? And so in this way, we have created the full Hamilton circuit without ever guessing anywhere, right? All of this was just straight up reasoning one step to the next. It's not a very clear and linear bunch of reasoning, but it is just, you can work this out rather than guessing anything. So the way to do this, you can work these out by choosing some edges. Then, based on those, you can exclude some, then exclude some, then choose some, etc. And hopefully, you can, by some sort of sequence of reasoning where I have to use these ones, that means I can't use these ones, but that means I have to use these ones, and so on. Do this enough times and you will create the Hamilton circuit, filling out the whole graph. This is the idea of the procedure. It's hard to describe just in simple terminology. What is the procedure? It's a matter of sort of working out the little details. All right, so I have one for you all to try. This is a somewhat bigger example. It's like this, and then I have some horizontals here, here, and here. And I'm gonna stick a vertex right in the middle of that one. All right, and your job here is to find a Hamilton circuit without guessing. Of course, if I'm grading this on the test, it's hard for me to tell if you're guessing or not, but find a Hamilton circuit without guessing. All right? Al will help us get started. Remember how we got started before, and that is every vertex which is degree 2 in the original graph, you must use those two edges. So for instance, in the upper left corner, this is a degree 2. You should just start by identifying. I don't actually care about any of the other degrees, but the ones which are degree 2 you should care about. And there's one other that's a degree 2 in this one, which is this vertex right in the middle there. And you can start by scribbling in all of the edges that meet the degree 2s. So my circuit must use this edge and this edge. It also must use this edge and this edge, right? It also must use this one and this one, and this one and this one, and these guys here, all right? So you have to, this is how you would get started. And now I would say from here, There are some which can be excluded based on the ones I've already chosen. And then given those exclusions, there are some which must be included, and so on. I'll let you try and take it from here. See if you agree with me that some at this point can be excluded. I'll walk around and see how you feel. Guess it.
Yeah.
All right. I would. It's eventually I'll ask you to do like really big ones where you'll be able to guess it. So you should see if you can work out exactly how it's going.
What's that?
Yeah. How did you figure that out?
Just
You guessed it.
yeah.
I would like you to try and do this without just guessing. Some people are just saying, oh, given where I start with those, I can just fill it in. But in general, you need to be able to do this on like perhaps very large graphs. And so it's not a good idea to just try to eyeball it from here and fill them in. You should try to reason it out by excluding certain edges and then including certain edges and so on. How's it going? You all caught up?
Trying to. Yeah. I'm not guessing.
That is not the picture that I drew.
I'm like, oh.
It's a little bit. It's like I'm not guessing. Draw it. Doing okay here? Yeah.
I'm just excluding one.
I think we excluded too many.
This one?
So I like this maybe that, I would say at this point, it's not clear. Should I use this one here or across the top? Yeah, so now, if you look here, there are three edges to it, but this is you have these two here. Just right here, it's two edges. All right, let's talk about this. I see some people are stubbornly refusing to work this out by any logical means, but you're gonna want to have some kind of way of actually thinking it through rather than just guessing the answer. Anyway, this is how you start, by scribbling in edges which meet degree 2s. And now I want to exclude some. And the idea is, if there's any vertex where I already used 2 of the edges, it means that you can't use any of the other edges there, because no three-way intersections are allowed. So I am looking, what you have to do, you have to look through this whole graph and see, can I find any vertices where I already used 2 of the edges? And then I should X out any remaining edges. And I see actually 2 like that. There's one here. Actually, I'm gonna, just for the sake of my notes, having it kind of in steps, I'm gonna copy this. I know this is hard to do if you're using normal paper, but now we are going to exclude if we see a vert with 2 red edges already. That means you cannot use any more edges at that vertex. And I see that here and here. You can't use those guys. It's because this vertex already has 2 red edges on it. You are not allowed to have a 3-way intersection in a Hamilton circuit, and that means that this edge is not allowed right there. And similarly, over here, it's the same situation. I have already used those 2 edges, so I cannot use this edge. All right? I think those are the only exclusions you can make at this point. As I was walking around, I saw some people, they were like, oh yeah, I should draw in this edge. And I said, why did you draw in that edge? And they're like, yeah, because I want to make it all like connected up. This is not a good reason, because there are many ways that you could make this all connected up, and maybe that was a bad choice. In fact, that was a bad choice. You should not make an edge right there. But anyway, I'm going to continue without making any guesses. At this point, does anybody see where I have done some exclusions, and now I can do some new inclusions? Anybody actually work this out logically? Looking at this picture, I can see some places. I'm going to copy it again just so we got the play-by-play here. I'm going to say include, maybe I'll write it in red. Include edges where only 2 are legal. I can see 2 vertices here, which actually only have 2 legal edges remaining. Anybody know what I'm talking about? Some of you allegedly did this. I can see 2 vertices where there's only actually 2 allowable, that is non-excluded edges left over. Anybody see? I would look at those 2 edges which I just crossed out and said I'm not going to use, for instance, this edge here. I'm not going to use that one. What does that mean about this vertex on its other end? Here, there are only 2 edges remaining which are possible to use, and so we must use those 2 edges. So I'm looking right here and here is the same situation on the other side. Maybe I'll get rid of those guys. At this point, there are only 2 allowable edges here. There's 3 total, but I already said I'm not going to use that one. That means I have to use the other 2. I hope that people are able to understand what I'm talking about here. Nobody's saying anything, which maybe that just means you don't want to say anything, which is fine with me. If this seems totally crazy to you, you're going to feel crazy when you try to do it on the test. So I hope that everybody is feeling okay about this. If not, let me know. We're going to do more examples, but some of you have this look on your face like, he better not ever ask me to do this myself. I definitely am going to ask you to do this yourself. Okay, so right here, you must use these two because there were only 3 to begin with. I have to use 2, and I already excluded this one. That means I have to use these 2. And similar over there, the same situation. There are only 3 edges here to begin with, but one of them has already been excluded. And so right over here, I must use the remaining 2 edges, here and here. All right? Great. Now I would say it's easy to guess how to finish this problem. You have to just use the edge across the top to connect everything up. But even so, just because I'm a guessing hater, you can actually reason this out all the way home. So I'm going to copy this again just so that I can say step by step what my reasoning is. Here, again, we can make exclusions at now this vertex and this one. They have 2 chosen edges already, which means the 3rd edge must be excluded. So over here, this one and that one are now excluded. So these are more exclusions at vertices where we already have 2. Right? Those 2 vertices that I circled in this step already have 2 edges that are chosen there, and so you can't use the 3rd one. And then finally, my last step would be, are there any places where there's only 2 legal options remaining? And if I look at this vertex here, there are 3 edges total. 1 has been excluded, which means I must use the other 2. Now, I already knew I was going to use this one, but that means I have to use this one also. So, and that, once I do that, it'll really be over. So my very last step is just at the very top here. So this time I'm looking at this vertex and this vertex, and I can see that at both of those vertices, I have excluded one of the options, which means I need to use the other 2 options. One of them is already chosen, but I also need to choose this one here. All right, so again, this is include this one, this edge on the top, all right? By all the same reasons as everything else that we have talked about so far. And this is done, right? This is now the Hamilton circuit. Don't tell me I could have just guessed that from the beginning. I think it's true, actually. Probably you could have just guessed that from the beginning. But you have to imagine doing this on a very, very big graph where you're not going to be able to just kind of visualize the whole thing at once. But you can still do these individual little steps to draw in more edges as you go. All right? Anybody got thoughts about this? You will have more practice with these on the homework. And we're going to do, we're not done talking about this, so we're going to do some more next time. In our remaining 5 minutes, so I can tell you about our second big notion. So all of this, really, this entire strategy that we've been talking about, remember, is basically just about this here. Every vertex meets 2 of the chosen edges, all right? What that means is if there's 2 and then there are more edges, you have to X out those more edges. And if you have a vertex where there's only 2 that you're allowed to use, then you have to use those 2, all right? That's all. The entire strategy is based on this one box. There's one more simple bit of strategy that will kind of do it for us in terms of strategies. So one more strategy. One more strat. And that is, once you draw a Hamilton circuit uses every vertex. That's what it means. And also is connected. I mean, a circuit has to be connected. This is an obvious fact. So it has no subcircuits. And I'll tell you what I mean by that in a moment. No subcircuits. This is the second basic fact which leads to these kinds of strategies for including or excluding edges. No subcircuits. For example, here is a very simple example. Maybe something like this. All right. Now, if you begin here by looking at the degree 2's, there are 2 degree 2's, that's here and here, which means I should start by using those edges and those edges, right? You have to use every edge that touches a degree 2. Would you mind, sorry, this is a lot easier for me than for you. I don't want both of these diagonals. Can I just take one out? Sorry about that. Is that annoying? I know it is if you're using a real piece of paper. All right. Now, how should we choose our next edge? This is the no subcircuits rule. It says, don't choose this edge right here. If you had chosen that one, it would make what we call a subcircuit. That is, all those ones makes a square, which is a circuit all by itself, but I didn't cover everything else, all right? So this right here shall be excluded because if we use that one, if we use this one, it closes up the circuit too soon, right? Because that would make a circuit right there, which didn't cover the entire graph. The idea is you have to cover all the vertices. So if we use this one, it closes up the circuit too soon, right? And that's called a subcircuit. If you were to use that one, it would close up the circuit before having hit all the vertices, and so it should be excluded. All right, so this no subcircuits rule is another way by which you can exclude certain vertices. Can we continue from here? Having excluded that one, can we finish drawing the Hamilton circuit? I'm gonna make another one down here. Whoa, whoa, whoa. Now, if I exclude that one, I can see at this vertex down at the bottom, now I used to have 3 edges there, but now there's only, I've excluded this one, which means I have to use both of these on the bottom. So here, I'm gonna have to use this one over here. And then what else should I do? Actually, I didn't notice this before. Now that I deleted the other diagonal, this is now a degree 2, which means we have to use this one and this one. All right, and there's my Hamilton circuit. Of course, you could have guessed this all the way from the beginning, but I'm trying to show how this no subcircuits thing can lead you to make these kinds of deductions. All right, we'll do a bunch more examples next time with the no subcircuits and such. See you then. Please let me know if you got homework questions. It's due tomorrow as usual.